Hello there, young students of chemistry. This is a quick addendum to the equilibrium constant recording from earlier. A couple things that I just neglected to mention that I think are important. So really, when we are talking about equilibrium, there's three general types of equilibrium. There is gaseous equilibrium, and that would be where you have reactants and products that are all gases, and the equilibrium is occurring in a closed container. And typically the equilibrium constant K is represented by a Kp, and that would be the equilibrium constant dealing with pressures. So because normally we measure amounts of gases by their pressure. We could also use Kc, which is the general equilibrium constant, and that C stands for concentration. Now, the other equilibriums that are present are equilibriums that occur in solution. So these are aqueous equilibriums. And there's a couple of types of aqueous equilibrium. There is acid equilibrium, and so we would write Ka, and we would call that the acid dissociation constant or the acid ionization constant. Remember that when an acid interacts with water, I'm just going to use Ha for my acid. According to Arrhenius, acids make hydronium, and weak acids reach equilibrium, where strong acids, that reaction goes to completion. So this is the general equation for an aqueous equilibrium of an acid. We could do the same thing with a base. Kb, of course, be our base. Instead of using OH, I'm just going to use a B for base. So base plus water. We know that strong bases, this reaction goes to completion, but weak bases, it reaches an equilibrium where it pulls a hydrogen from the water to make this Hb, and then we have hydroxide ion that is formed. So the last type of aqueous equilibrium is what we call solubility product equilibrium. SP stands for solubility product. And that would be when we have a precipitate that is formed and then dissociates very slightly in water. So what we have here is a salt or a compound. I'm just going to call it YX, which is solid. And that's going to dissociate. We know that compounds that are really soluble will dissociate completely. Compounds that are kind of insoluble dissociate just a little bit. So we're talking about aqueous ions here, except for our precipitate, the YX. So it's important that you know kind of the words that go along with this. Remember that the equilibrium constant is calculated using the law of mass action. So we would have K is equal to the concentration of the products raised to the power of their coefficient divided by the concentration of the reactants. And since the value for the equilibrium constant is products over reactants, we know that the equilibrium constant is directly proportional to the amount of products we get. So the larger the value for K, that means that there's more products. It tells us the extent to which the forward reaction goes. When I say forward reaction, I'm saying the reactants colliding to make products. The reverse reaction is the products colliding to make reactants. So the larger the value of K, the more products we get. So just as that applies to acids, if we have acids that have particular values for equilibrium, if you have a value of the acid dissociation constant, let's just say there's 2.4 times 10 to the negative 4, compared to a Ka, an acid dissociation constant of maybe, I don't know, 1.6 times 10 to the negative 10. The value that has the equilibrium constant that is larger means there's going to be more products. meaning there's going to be more hydronium. And the more hydronium we get, the better the acid is. I don't want to say it's strong, because it's not, but it does produce more hydronium, which means it's a better acid. So you can use Ka values to compare acids to each other. We can see that 2 times 10 to the negative 4 is a much larger number than 1.6 times 10 to the negative 10. So if this is for acid 1, we would go, okay, this acid is a better acid than this acid is. So it's important that you can make that distinction between Ka values. The same would apply for the base dissociation constant. The larger the value for Kb, the more hydroxide that compound is going to make. It's going to be the better the base. For Ksp, we can see that in the forward reaction, what we have is solubility. So this is dissolved. This is not dissolved. All right? So if we have large values for Ksp, that means that it's going to make more products. The larger the value of K, the more products we're going to get. And in this case, that means there's going to be greater solvation. There's going to be a greater solubility for that solubility product. So again, we can use solubility product values to determine how soluble is the salt. Large values of Ksp mean that the salt is more soluble. It's making more ions, and that's what solubility is. So just a little follow-up there, how we can use equilibrium constants to make some general comparisons regarding equilibrium conditions.